Hello, my name is Joseph Daron and I'm a researcher at the Climate System Analysis Group at the University of Cape Town. Together with my co-author David Stainforth from the Grantham Research Institute at the London School of Economics, we've written a paper titled On Predicting Climate Under Climate Change. The paper questions how we design and interpret climate model experiments when aiming to provide climate predictions on timescales from tens to hundreds of years. We conclude that even if a model were a perfect representation of reality, current approaches to climate modelling are inadequate for providing robust probabilities of future climate change. Our results are important for how we quantify uncertainty in climate predictions and also for how we use climate model output to inform adaptation decision making.
We begin our letter with a central guiding question. Can today's global climate model ensembles characterise the 21st century climate in their own model worlds? To answer this question, we first examined some of the conceptual issues relevant to climate prediction.
Perhaps the most important and fundamental of these issues is how we define climate. We contrast two competing definitions. One common approach takes the distribution of weather over a period of time, typically 30 years, to define climate. Alternatively, from a nonlinear dynamical systems perspective, we might consider an attractor to represent the climate. Here, the atmosphere-ocean state at any point in time can be described by a point on the attractor, while the climate is the entire distribution of states across the attractor. In climate modelling, if we adopt the first definition, we require time series data to populate our climate distributions. And if we adopt the second definition, then we require ensemble experiments from multiple initial conditions. If we assume that the two approaches will yield the same distribution, then we are making what we refer to as the kairotic assumption.
Using a low-dimensional, non-linear system with characteristics of the coupled atmosphere-ocean system, we explore the consequences of adopting these two different conceptualizations. Our model is the Lorentz 84 model, which represents some aspects of the atmospheric circulation, coupled to the Stommel ocean box model. In this figure, the top left panel shows the attractor of the model for the ocean temperature and salinity variables, and the top right panel shows the atmospheric variables x, y and z under certain fixed forcing conditions. The two panels at the bottom show the attractor for a different set of forcing conditions used later in our analysis. The small red spheres show the locations of the initial conditions used to create the ensembles used in our study.
Using single model trajectories and initial condition ensembles, we first examine the length of time it takes to reliably quantify the climate distributions of our model under stationary forcings. We find that ensembles are able to quantify the climate of our model more quickly. So far so good, but in predicting climate under climate change, we're interested in the errors introduced by using time series data of a single or small ensembles of simulation to quantify an evolving climate.
This figure shows how the climate of our model for ocean temperature and salinity variables evolves under different forcing scenarios. The top two panels show in blue how a very large initial condition ensemble spreads out and converges to a stable distribution. The line in orange provides an exampled single trajectory. We show that using data from single time series or small ensembles can lead to errors of more than 20% when compared with the large ensemble data. The middle and bottom panels show scenarios which parallel climate change, where a modelled parameter is slowly changed over 100 years and then remains constant. Here, we find that the errors resulting from a temporal definition of climate can be even larger. Furthermore, even when larger ensembles are available, temporally derived distributions can converge to the wrong climate distribution.
We are currently considering ways to replicate these experiments in operational climate models, which are, of course, considerably more expensive to run. However, the results in this paper show that choices in how we design and interpret model experiments can have a substantial impact on the probabilities we derive for future climate. This is crucial information for how we use such results to inform policy and guide adaptation decision making. I hope you found this introduction to the paper informative, and if you'd like any additional information, please don't hesitate to get in contact. Thank you very much for listening, and I hope you enjoy reading the paper.